This is video number 3 from module 2, wrapping it up with cyclohexanes. Cyclohexanes offer us a good opportunity to look at some new concepts, and also they're very, very common in nature, so of high importance. If you flip through your organic book, you'll see lots and lots of molecules that incorporate cyclohexane rings. The way we've been drawing trans 1,2-dimethyl cyclohexane is like this. But if you build a model of this, you'll find it's not a very realistic look at what the molecule really looks like. Looking at carbons 1 and 2, see how if you build the model, it looks much more like this, with the methyls sort of slightly offset, but notice they're still trans. So we want to start to be able to draw cyclohexanes in this conformation, which is called the chair conformation. And it's the most stable conformation of the molecule. So conformational analysis takes into account how rings can flex and how bonds can rotate, leading to different energy levels, energy conformations of the molecule. And this becomes important in activity and reactivity of molecules. So you don't have to be Michelangelo, but you should be able to draw a chair conformation because all it is 6 lines. 2 parallel lines like that is how I would start. A longer line angling down, followed by a shorter line angling up, and then reverse that process below. Longer line angling over, shorter line. And there's a nice chair conformation. You want to be able to duplicate that through practice. If I draw a chair conformation of the molecule you see here on the right, I'll draw my chair. You get good at it after a while. In position 1, you draw a line straight up. In position 2, straight down. And you just start alternating like that. Straight up, straight down, straight up, straight down. And if you build a model, you'll see that that's the angles that they're at. 1, 2, 3, 4, 5, 6 is how the compound's numbered. Then to fill out the other bonds, you have slightly down, slightly up, slightly down, slightly up, slightly down, slightly up. No, that doesn't look good. Slightly up. So this is the correct way to draw a substituted cyclohexane. As I've drawn it here, you notice if I don't say otherwise, every one of these terminals of lines is a methyl group. But that's not what this molecule is. What I want to draw is a methyl here and a methyl here. And since I don't want any of these other ones to be methyls, I have to draw in H's. If I draw the lines, I have to draw the H's. I could have left the lines off like you see at the right. So here's where there are methyls at the 1 and the 4 position. If you do the ring flipping, you can get to a boat conformation from a chair conformation. But this is higher in energy. And the molecule really won't want to stay in this position. In fact, we can analyze the energies as you do all the flips and not rotations, but just flips and flexing of the ring. And following that, you'll see from the chair conformation, which is the lowest energy, it'll pass through a really high energy state called a half chair. You could try to duplicate that with your model set. Then it'll flex back down to a twist boat, which is lower in energy, a boat that's higher, and so forth, until you get all the way back to the most stable chair conformation. And the way to think about this is that it's going to spend most of its time in one or the other chair conformations. Notice they sort of like lean toward each other and look as if they're looking at each other in the mirror. But these changes occurred just through flexing and flipping bonds, and anything that's cis to something else or trans to something else will stay cis or trans. But axial and equatorial positions will shift. So axial positions are defined here as the ones that are straight up and down. Equatorial defined here as all the ones that are sticking out, sort of like at the equator of a planet, right out around the waist, around the midsection. So these are all the equatorials. Ring flipping, like I said, exchanges or interchanges. All the axials will go equatorial. All the equatorials will go axial. So here's some dramatic footage of that. It'll go through the iteration several times. Notice here all the blue are axial to start with, and the reds are equatorial. If you hold down one side of the molecule and flip the other, and then do the same to the other side, notice all the blues are now equatorial and the reds went to axial. So it's going to go through this again once or twice, just so you can see. Okay, so the larger a substituent is, so maybe looking at an ethyl group here in the axial position, it will start to experience an interaction with other substituents that are axial. And notice the numbering of the carbons makes this a 1,3 diaxial interaction. And it's an unfavorable interaction, energetically speaking, because these groups that are axial at this distance apart are actually much closer than it appears here. So the larger the group, like an ethyl group, and don't forget this can rotate freely around a single bond. So it's sort of spinning like a propeller here and banging into this hydrogen. And so larger groups will try to avoid this. And notice there's another axial substituent here at 5. So technically speaking, it ought to be 1, 3, 5 triaxial interactions, but I think I prefer the 1, 3 diaxial actually. So because of this unfavorable energy interaction, larger groups will prefer to stay equatorial, and they can do so by ring flipping, just like we saw above. So if all the axials, like these two methyls in this case, in the high energy form, flip to equatorial, and all the equatorials flip to axial, you end up with this lower energy form, which has an error in it. This should be methyl right there, and down on the other part, it should be just a hydrogen there. Quickly correcting it. So there, notice this is di-equatorial. A molecule like the one you see here probably can't get to other conformations. With this gigantic tert butyl group and this methyl group, I doubt that these can be that this can ring flip to where those are both axial. So it gets to a point where the molecule will be more locked in one conformation versus another. Other molecules can be locked into one rotation versus another. It's called restricted rotation. So in the next module, we're going to continue with conformational analysis. Conformations being flexing, twisting, rotating, things like that. Not changing the molecule, not making isomers, right? Because remember that involves detaching and switching bonds. Okay. So if we, like the example of a kind of analysis that we're going to do is if you look at these 3 bonds on the carbon in back at carbon 1, and then if you look at these 3 bonds here in front, carbon 2, and if we bring these down into the drawing below, you'll see that these are in front and these are in back. And if you imagine that back carbon as being a bigger circle, which I've always thought was maybe backwards of what it should be, but in any case, the back has the bigger circle. This allows us to analyze the angles between the substituents. So, for example, this angle would communicate to us that those 2 groups, it'll indicate to us the distance apart of those 2 groups. So we're going to do a whole lot more of this kind of thing in the future. And notice here we have where it's connected there and there to the remainder of the ring. So this is a projection view. All right.